Did you know that light takes 4 years to reach the Earth from the star closest to us after Sun? And that there may be trillions of galaxies beyond the edge of the universe whose light has still not reached us. We'll learn about all these cool facts and many more in this video. Let's begin. We live on a planet, one of many around a star, which is one among 400 billion others in our galaxy. Our galaxy, the Milky Way, is one among trillions of other galaxies that we can observe, and yet we are aware that even this unimaginable number might just be a small fraction of the entire extent of our universe, because we can only see objects the light from which has already reached us. The unprecedented scales in the universe imply that we must use different yardsticks to measure distances on different scales. In this video, we'll overview some of the methods used for measuring distances in the near and far universe, concluding with our current understanding of the scale of the universe itself. The set of overlapping methods by which astronomers establish a distance scale for objects in the universe, from nearby planets to the most remote galaxies, is known as the cosmic distance ladder. Distances are essential for estimating other properties such as the size and luminosity of astronomical objects. At every step of the distance ladder, uncertainties can creep in. In addition, each step inherits problems of the ones below, such that the errors intrinsic to each step become larger for the more distant object. While the distances within the solar system are known to much greater accuracy, the distances to remote quasars are highly uncertain because they depend upon our understanding of the expansion of space and the accuracy of the cosmological parameters such as the Hubble constant. Let's start with an analogy of measuring distances on Earth using simple trigonometry. Imagine an observer looking at a distant tree from a position A such that the angle made by the sight line is A1 as shown. Now, if the observer moves some distance d along the baseline, the apparent position of the object appears to have changed with respect to the observer and makes an angle A2 with the baseline. By knowing the distance moved by the observer and the angles A1 and A2, we can measure the distance to the tree using trigonometry. This method is called triangulation. The small apparent change in the position of the object with respect to the observer is called parallax. You can easily demonstrate this phenomena by looking at your thumb with an arm stretched out against the backdrop of other distant objects, say a painting on the wall. The shift in the position of your thumb when you close one eye followed by the other is parallax. Similarly, in the course of a year, as Earth revolves around the Sun, the position of the nearby stars seems to shift relative to distant stars. This is known as parallax. We know that every 6 months, the Earth moves nearly 470 million kilometers from one side of its orbit to the other. This is enough to give us slightly different lines of sight to a nearby star seen against a backdrop of more distant stars in the background. The parallax shift is extremely tiny, less than an arcsecond. As an analogy, consider that an arcsecond is the angle made by a football kept at a distance of around 45 kilometers from you. The full moon subtends an angle of just over half a degree, which is 30 arc minutes. An arc minute is equal to 60 arc seconds. From the ground, trigonometric parallax is limited to parallax angles greater than 0.01 arc seconds and therefore yield distances only to stars within a radius of about 30 parsec from us. This limitation is due to the fact that farther an object is from the observer, the smaller is the angle it subtends at the position of the observer. And even though 0.01 arcsecond may seem like a very tiny number, remember that we are talking really large astronomical distances. For reference, Alpha Centauri, the nearest star to us beyond the Sun, subtends an angle of only 0.77 arcsecond, even though light emitted by it traveling at a velocity of nearly 300,000 kilometers per second takes over 4 years to reach us. The concept of parallax gives us an opportunity to devise a more convenient way of measuring distances. A parsec is defined as the distance from which the radius of Earth's orbit subtends an angle of 1 arcsecond. Going by this, Alpha Centauri with a parallax angle of 0.77 arcseconds has a distance of 4.2 light years or around 1.3 parsec. Launched in the year 1989, the European Space Agency's Hipparcos satellite was the first space mission dedicated to measuring the positions, distances, motions, brightness, and colors of stars. Such measurements of light, which are related to the position of objects in space, are known as astrometry. Hipparcos observed more than 99% of all stars down to a visual magnitude of 11, which is almost 100,000 times fainter than the bright star Sirius. With the help of parallaxes measured with a precision of less than a millisecond, Hipparcos enabled astronomers to measure distances to stars up to around 300 parsec, going 10 times deeper than the ground-based observations. Hipparcos has now been succeeded by the Global Astrometric Interferometer for Astrophysics, or the Gaia satellite mission. Amongst others, Gaia has greatly improved parallax measurements and added in millions of more very faint objects by observing the sky over and over again. The distance between Sun and the Earth is one astronomical unit. But did you know that the same concept of parallax was used to measure the value of one astronomical unit in the 18th century? In the year 1761, astronomers witnessed a rare cosmic event, the transit of Venus. By making some measurements and using trigonometry, they were not only able to measure the value of one astronomical unit, but also postulate that just like Earth, Venus may also be surrounded by an atmosphere. The measurements were based on very simple principles. Imagine two observers, one at each pole of the Earth, viewing the transit of Venus. The person at the North Pole sees Venus following one path across the Sun, while the person at the South Pole sees Venus follow a slightly different path. Assuming Sun is a circle, the two different paths will have different lengths. A simple way of measuring the lengths of these two paths is to time the transits using the four phases of the transit as indicators. With the two different paths known, the distance between the Earth and the Sun can be calculated using trigonometry and Kepler's third law of planetary motion. The Kepler's third law states that the square of the orbital period of a planet around the Sun is proportional to the cube of the orbit's semi-major axis. This law had allowed Kepler to establish that the distance between Earth and Sun is around 1.39 times the distance of Venus from the Sun. Let the angle between the two paths measured from Earth to be E as shown here. This distance relationship leads us to angle V, the angle between the two paths as seen from Venus. This angle V is 1.39 times of angle E, or angle E divided by 0.72, assuming that both the angles are very small. Besides angle V, the only other thing we need to know is the distance between the two observers A and B on Earth. If this distance is DAB, then we can apply basic trigonometry to get the distance from Venus to Earth. As seen here, a right triangle is formed between Earth and Venus, using which one can calculate the distance between them. Once the distance between the Earth and Venus is known, the distance from the Earth to the Sun can be calculated using the Kepler's third law again. This implies that the distance between the Earth and Venus is 0.28 times the distance between the Earth and the Sun. That is, the distance between Earth and Sun, which is one astronomical unit, is around 150 billion kilometers. Now, with the advent of technology, we can use the knowledge about the speed of light to measure distances to objects in the solar system. Light travels with a velocity just under 300,000 kilometers per second. Lunar laser ranging, or LLR, is the practice of measuring the distance between the surfaces of the Earth and the Moon using laser. The distance can be calculated from measuring the time taken by the laser light to complete a round trip from Earth to the Moon's surface and back, or by one of several retroreflectors installed on the Moon. The calcium-2K line in cool stars is amongst the strongest emission lines which originate in the star's chromosphere. In the year 1957, Olin C. Wilson and M.K. Vainubapu, who is fondly known as the father of modern Indian astronomy, reported on a remarkable correlation between the measured width of the calcium-2K line and the absolute visual magnitude of a cool star. This effect, now known as the Wilson-Bapu effect, is independent of the spectral type of stars. It is applicable to main sequence stellar types G, K, and red giant stars of type M. The greater the emission band, the brighter is the star. By using an empirical correlation, such as the one shown here, and measuring the apparent brightness of a star, the distance to the star can be determined. This method has been shown to work for stars within 100 parsec of the Sun, although with a sizable error of around half a magnitude in the absolute brightness and therefore significant uncertainty in the measure of the distance. Further out from the Milky Way, we require indirect methods to measure the absolute luminosity or distance of stars to measure the true distance. Now we know that most of a star's lifetime is spent on a well-defined track called the main sequence in the temperature-luminosity plane, also known as the HR diagram. Towards the end of its lifetime on the main sequence, a small fraction of stars with well-defined combinations of luminosity and temperature begin to oscillate radially such that their size is no longer correlated with their luminosity. It turns out that the resulting period luminosity relation for these variable stars is so well defined that it can be used to measure extragalactic distances to such stars, and therefore the galaxies in which they reside. Delta Cepheid stars, also known as classical Cepheids, are one of the three different types of pulsating stars which have a well-defined period luminosity relation, making them ideal for measuring distances. Cepheids are young stars often found close to the disk of galaxies in young star clusters. Polaris or the pole star is the closest pulsating variable at a distance of around 200 parsec. In March 2024, the farthest Cepheid was discovered in the spiral galaxy NGC 5468, which is located at a distance of around 40 megaparsec from us. Astronomers made use of the data from the Hubble and James Webb Space Telescope to make this outstanding discovery. Cepheids are population 1 supergiants of spectral class F to K. They have a time period of 1 to 50 days with amplitudes ranging between 0.1 and 2.5 magnitude, varying through the cycle. The shape of the light curve is regular, showing a fairly rapid brightening followed by a slower fall-off. Around 1,000 Cepheids are known in the Milky Way, the brightest of which, OGLE GDCEP 1884, was recently discovered and has a period of over 78 days. The relationship between the period and luminosity of a Cepheid was discovered by Henrietta Leavitt in the year 1912 using the Cepheid variables in the Small Magellanic Cloud. The pulsation period is related to the mean density of the star. On the other hand, the size of a star and hence its mean density is related to its total luminosity. The relation between luminosity and logarithm of the time period p is linear as shown here. Beside measurement error, the departure from a straight line are a consequence of the fact that to some extent the luminosity of the Cepheids also depend on color because we know that bluer stars are brighter. Therefore, for accurate determination of distance, this effect should also be taken into consideration in case of Cepheids. To measure distances using the period luminosity relation of the Cepheids, the period of the star is measured by continuously monitoring its apparent brightness. The period luminosity relation is used to predict the absolute or intrinsic brightness, which is then plugged into the luminosity equation to find the distance to the star. Since Cepheids are visible to great distances, up to 40 megaparsec at the time of recording this video, they can be used to find distances to nearby galaxies. There are in fact two types of Cepheids, the classical Cepheids and the W Virginis stars. Both types obey a period luminosity relation, but the W Virginis stars of a given period are 1.5 magnitudes fainter than the corresponding classical Cepheids. This difference is due to the fact that the classical Cepheids are young population 1 stars, whereas W Virginis stars are older stars of population type 2. Otherwise, the two classes of variables are similar. The rotational velocity of spiral galaxies is correlated with their luminosity. This empirical relation can therefore be employed to find the apparent magnitude and consequently the distance to nearby galaxies for which the rotational velocity can be determined. The rotational velocity is found to be proportional to the luminosity of a spiral galaxy such that the brighter galaxies rotate faster. By measuring the apparent brightness and rotational velocity of several galaxies, say in a cluster of galaxies, astronomers can find a linear correlation for the cluster. If the same exercise is repeated for a number of clusters, the Tully-Fisher relation can be used to determine the relative distance between different clusters, or if the distance to any one of the clusters is known, the absolute distance to them. Supernovae are some of the most energetic cosmic events. Within a few days, the luminosity of the exploding star, aka the supernova, can reach up to 1 billion times the luminosity of the Sun, which is a significant fraction of the luminosity of all the stars put together in a galaxy. After the peak luminosity is reached, the brightness of the star continues to decline again for a period of several weeks. Most of the higher order elements that we are made up of are produced in supernovae explosion, which then enrich the surrounding interstellar medium. The supernova 1987A was the first naked-eye supernova visible since 1604. It is a type II supernova in the Large Magellanic Cloud. This image shows a montage of images of this supernova taken over a period of almost a decade, which shows how the luminosity of the supernova has changed and the structure around it has evolved during this time period. The distinction between different types of supernova was originally based on their spectral properties. Type I supernovae do not show any Balmer lines in their spectra in contrast to Type II supernovae. Type 1a supernovae show strong silicon II lines in their optical spectra, whereas no such lines are present in the spectra of Type 1b and Type 1c supernovae. Observations have now established that Type 1a supernovae are intrinsically different from others, such that Type 1b, Type 1c, and Type 2 supernovae are associated with younger stellar populations, while Type 1a are linked with older stars. Our current understanding of their formation mechanisms imply that they must be found in spirals as well as ellipticals, making them ideal yardsticks for measuring cosmic distances. Type 1a supernovae occur in binary star systems in which at least one of the stars is a small white dwarf star. The dwarf accretes and eventually accumulates enough material from its neighboring giant star, causing a chain of nuclear reactions which ultimately result in a massive explosion which destroys the parent white dwarf star. The various colors observed in the explosion correspond to distinct elements being produced in the supernovae. The Type II supernovae, on the other hand, are a result of the final stages of massive stars. After a star with typical mass of 20 solar masses or higher loses its ability to fuse any more elements in the core, it can no longer sustain thermostatic equilibrium between the expanding outer shell and gravity contracting its core. As a consequence, the core collapses on itself, leading to an increase in temperature and density at the center, causing it to quickly rebound, which releases the outer layer of the star with a loud bang that we observe as a supernova. A white dwarf star which explodes into a Type 1a supernova is formed from low-mass stars. Prior to the explosion, the pressure in such a star is maintained by electron degeneracy pressure, which is a quantum mechanical phenomenon. Such a star can be stable only if its mass does not exceed 1.44 solar masses, as discovered by Indian-born astrophysicist Subramaniam Chandrasekhar. Chandrasekhar, together with William Fowler, won the Nobel Prize in Physics in the year 1983 for their discovery. By the way, NASA's X-ray satellite mission is named Chandra to honor him as well. If the mass of the white dwarf star exceeds the Chandrasekhar limit, the degeneracy pressure can no longer balance the gravitational force and the core of the star begins to collapse, immediately followed by an explosion, as in the case of Type II supernovae. Since the conditions required for the white dwarf stars to explode as a Type 1a supernovae are so homogeneous, it is likely that they all reach the same maximum brightness. This leads to their usage as standard candles for measuring cosmological distances. As shown in the examples here, supernovae often appear as bright stars against the backdrop of the fainter host galaxy. Repeated observations are used to sample the luminosity of the supernovae at different stages of the explosion. Any object in the universe whose intrinsic luminosity can be estimated with high precision is called a standard candle. The knowledge of apparent and absolute brightness of such an object can be used to measure its distance from the observer. As it turns out, supernovae are at best standardized candles. That is, their peak brightness varies by around 0.4 magnitude in the blue band. If supernovae were standard candles, all the data points in the top plot would line up along the straight line as described by the Hubble's law. However, do notice that there is a strong correlation between the peak luminosity and the shape of the light curve. As it turns out, supernovae with higher peak luminosity decline more slowly relative to their counterparts. Also, the measured luminosity may be affected by dust present in the Milky Way or the host galaxy. By combining the impact of these factors, astronomers have devised empirical corrections which can be calibrated by applying them to the light curves of supernovae, for which the distances to the host galaxies are very accurately known through other methods. As shown, this greatly reduces the tension between the supernovae data and the predictions of the Hubble law. Supernovae are therefore standardized candles where the standardization is done with the help of observations in multiple wavebands to account for various factors such as dust. Once the luminosity is measured, the luminosity-distance relation can be put to use to find the distance to the host galaxies. In the past few decades, two large international projects searched for supernovae in high redshift galaxies. The High-Z Supernova Search and the Supernova Cosmology Project detected and observed supernova in many distant galaxies. Both these projects independently arrived at the conclusion that the universe is not just expanding but accelerating, and were granted the Nobel Prize in Physics in the year 2011 for their discovery. Their results, first published in a paper in the year 1998, completely changed our understanding of the cosmos because it meant that there exists an unknown dark force which is pushing the space and everything within it away from each other. Since we can't see this inexplicable force, but only experience its nature which opposes the attractive force of gravity, this ubiquitous force was named the dark energy. The farthest supernova ever discovered so far is the supernova 1997 FF, which is believed to be in a galaxy at a redshift of 1.7, that is, at a distance of more than 5,000 megaparsec away. This implies that the star actually exploded more than 10 billion years ago when the universe was only a quarter of its present age. That is the power of light. It not just allows us to see distant things, but also allows us to look back in time. New supernovae are continuously being discovered with improved observing facilities. For instance, this plot from Adam Rees and collaborators from their 2007 publication shows the relationship between the redshift and distance modulus of supernova discovered from the ground and by the Hubble Space Telescope. Which brings us to the question of how far back in time can we actually see. The estimated age of the universe is around 13.8 billion years. So, intuitively it might appear that the farthest we can see from Earth are objects from which light has taken 13.8 billion years to travel to us, which is a little over 4.2 megaparsec. But that is not correct, because in accordance with the Hubble's law, as the universe expands, the space is stretching with it. In other words, the fixed distance between two objects, known as the proper distance, is stretching with the space, just like the distance between raisins in a rising cake. The rate of expansion of the universe is determined by the Hubble constant, the value of which is debatable but lies somewhere around 70 kilometers per second per megaparsec at the present epoch. This means that two galaxies separated by 1 megaparsec are receding from each other with a speed of 70 kilometers per second faster due to the expansion of the universe. But we still do not know if the universe is flat or round, finite or infinite, and although that is immaterial to the fact that it is not just expanding but accelerating, the choice of the cosmological model plays a crucial role in determining the cosmological parameters such as the critical density of the universe and the Hubble constant. For instance, in the earlier phases of the history of the universe known as the matter era, the impact of dark energy on the expansion was negligible. In such conditions, assuming the universe to be flat like a very large or even infinite sheet of paper which is ever expanding, the present horizon distance comes out to be around 16.3 gigaparsec. But in the following epoch, when dark energy began to dominate the expansion, the distance to the horizon is estimated to be around 14.6 gigaparsec. Furthermore, it is possible to calculate that the proper distance to the object which will ever be observable to us on Earth is 19.3 gigaparsec. What it means is that everything within a sphere of radius 19.3 gigaparsec will eventually be visible to us, whereas the universe beyond that will forever be hidden from our view. To summarize, a range of distance indicators are required to measure cosmic distances on different scales. And although we have made considerable progress, a lot remains to be discovered. I hope you learned something new today. Do let me know in the comments what other topics you would like me to cover on this channel. I'll see you next week. Until then, take care.